I will present our paper Learning Attention as Disentangler for Compositional Zero-Shot Learning on CVPR 2023 by Shaozhe Hao, Kai Han, and Kenneth Wang. We tackle the problem of compositional zero-shot learning, aka CZSL. Given images that contain same visual compositions, we group them by the same attribute like yellow and the same object like flower. We aim to learn their shared concept and combine them into the unseen composition, that is, yellow flower. The baseline of CZSL is simply to learn a model to classify an image to an attribute and object composition by cross-entropy. We present our ADE model. First, we use a self-attention module to extract the composition feature. Moreover, we add two images that share the same attribute or the same object. We introduce two cross-attention modules that disentangle the shared visual concept. In this way, we can separately predict the concept from a pair of images. Let's delve deeper into our ADE model. Given an image of a red bus, we aim to project it from the visual feature space into the word embedding space, and classify the image into red attribute and bus object. First, the target image is fed into a frozen dino pre-trained VIT, producing encoded visual features. A composition self-attention is used to extract the composition feature, VC, and the composition embedder PyC projects the visual feature to the word embedding space. In word embedding space, we use a linear layer to combine the attribute embedding and the object embedding, producing WC. A simple cross-entropy is adopted for optimization. Our core contribution is to disentangle attribute and object concepts with a simple cross-attention mechanism. Specifically, we add two auxiliary images that share the same attribute or object. Given paired inputs, two cross-attentions, one for attribute and another for object, extract the concept's exclusive features, and two embedders respectively projects them into the word embedding space. In the word embedding space, we directly learn the attribute or object embeddings using cross-entropy losses. We totally leverage 5 cross-entropy losses to align the visual features to the word embeddings in 3 spaces, namely the attribute space, the object space, and the composition space. Therefore, we can formulate the cross-entropy loss. We use query key swapping for the cross-attention modules. Specifically, self-attention takes a single input as both the query and key. Cross-attention takes 2 different inputs, one for the query and another for the key. The output attends to the shared information from 2 inputs. We further swap the roles of query and key to derive 2 concept-attended outputs, which imposes equivalent cross-attention effects onto the 2 inputs. In addition, we also introduce a novel regularization based on the Earth's moving distance, aka EMD. Suppose we have supplies of NS sources and demands of ND destinations. Given the moving cost Cij from the ith source to the j's destination, an optimal transportation problem aims to find the minimal cost flow Fij from sources to destinations. We can formulate EMD for this problem. We will introduce an attention level EMD in our method, where the greater EMD means the closer distributions, that is, the attention is more focused on the concept. Assume you have 2 images like a white dog and a white cat. We want the EMD from the attribute attention to be large, because the attributes are the same. We want the EMD from the object attention to be small, because the objects are different. We can formulate the regularization term with these 2 EMDs for attribute sharing images. It also applies to object sharing images by reversing 2 EMDs. Specifically, given 2 inputs respectively used as query, we input them into the attention layer. We can derive 2 cross-attention maps. We average the position token map and use it as the Cij. We further use the class 2 position logits as the Si and Dj, which can fit into the EMD formulation. Our final training objective is the cross-entropy loss with the regularization term. In inference, we synthesize attribute, object, and composition probabilities to model the final prediction. The hyperparameter beta is tuned on the validation set to make the best prediction trade-off between the generalized composition and the independent concept. We compare our model with the state-of-the-art methods using multiple CZSL metrics. We first show the comparison under the closed-word evaluation. That is, we evaluate on a predefined composition subset. Our model significantly outperforms the others. We also compare the models under the open-word evaluation, that is, on all compositions. Similarly, our model outperforms the others. We show the scene-on-scene accuracy curve on CGQA. The x-axis denotes the scene accuracy and the y-axis denotes the on-scene accuracy. Our core metric is the area under the curve, that is AUC. The curve of our model is marked in blue. Our model can be used for text-to-image retrieval. For example, given 3 texts of scene compositions, we can retrieve the top 5 nearest images. We can also retrieve the top 5 nearest images for texts of on-scene compositions. In addition, our model is also applicable to image-to-text retrieval. For example, given 4 images of scene compositions, we can retrieve the top 5 nearest texts. Although some of the retrieved texts are not the ground truths, they are significantly reasonable descriptions for the image. We also test on images of on-scene compositions. Given 4 images, we can retrieve top 5 texts, which are all semantically related to the target image. Our model is able to disentangle visual concepts, allowing visual concept retrieval. Specifically, given an image of a yellow skirt, our model can disentangle the attribute yellow and the object skirt. We can respectively retrieve the top 5 nearest images for the attribute yellow and the object skirt based on the concept-exclusive feature. Here is another example of pink pants. Thank you for your time. Try our code and model, and welcome to our poster at Wednesday PM 282.